Hi, and welcome to another episode of Casual Learning. I'm your host, John Bannan. What's the deal with the divisibility of time? Uh, the question is Is time divisible infinitely for any given unit of time? Can you cut time into smaller and smaller and smaller segments to an infinite extent? Now, the answer to that is no, you can't. Time is quantized, or it comes in a small indivisible unit of time. And I'm going to explain to you uh, why I think that that is the truth. Uh, Under the general theory of relativity created by Albert Einstein, there is an inverse proportional relationship between time and velocity. So, as time decreases or slows down due to the curvature of space time, the object speeds up, its velocity increases. And this has the effect of an accelerating force that we call gravity. So, the velocities of an object plus the speed in which it travels through time always has to equal the speed of light. So if the speed of time, the time in which it's traveling, the speed at which it's traveling through time slows down, the velocity of the object must increase because those things always have to equal a constant, which is the speed of light. So as something goes near a massive object and its space-time geodesic is curved by that massive object's effect on space-time, uh, closer it gets to that massive object, its time slows down, and consequently, the object itself has to accelerate or speed up. Its velocity has to increase, uh, and this is what we call gravity. All right. So there is this intimate connection under general relativity between time and the velocity and acceleration of things through space. Uh, so that's an important thing to understand. So what does this got to do with is time indivisibly, infinitely indivisible or infinitely divisible? Sorry. Well, you can think of an object that is approaching a massive object and whose time is slowing down because of the curvature of space-time surrounding the massive object it's traveling to. And you can think of that in terms of like a timeline, for instance. So here's an object. It travels a certain distance. Okay, this is before its time slows down. And you know, in 1 second's time, from 0 seconds to 1 second, it travels a certain distance through space. But as it approaches this massive object that affects space-time and the curvature of space-time, uh, its time slows down. But consequently, its velocity also increases. So it ends up traveling a greater distance. So what happens then? This object, let's just say, ends up traveling twice the distance because its time has slowed down significantly. So you have these two situations. The slowdown in time is causing a greater increase in velocity and a greater distance in which the object travels. However, the time is the same. It took it a second. Both situations, it took a second. Now, if something travels this farther distance in a second, we say it's traveling faster. But its velocity could increase due to a slowdown in time. But so the time is the same. It's the same, but the distance is greater. Now, if you were to consider the idea that time can be divided infinitely into infinitely smaller and smaller segments of time, you would have a situation like this. Okay, I'm just cutting this time down in halves on both sides. So this is the midpoint, and this is the midpoint. This quarter point, this is the quarter point. Now I'm dividing these segments even further. However, you should notice that you could divide this segment an infinite number of times. Now, I obviously can't draw an infinite number of segments, but theoretically you could do that on a timeline like this. And each of these segments they're called an infinitesimal. That's what they're called in mathematics. So that an infinitesimal is an infinitely small segment. It, but over here, you can do the same thing. Divide this an infinite number of times, and those would also be infinitesimals. But hopefully you can see the problem here, which is these two things up here are not the same. These are not the same infinitesimals. These infinitesimals here are bigger than these infinitesimals here. See that? There's more space that's taken up here than there is up here. So those are larger infinitesimals. But infinitesimals don't have a size. So they can't be larger. So there's a problem here. These infinitesimals are not the same as these infinitesimals. There's an identity problem here. Um, so, you know, if you take this line and you divide it an infinite number of times, and this is the same amount of time as this, the number of infinitesimals in here has to be the same as the number of infinitesimals here. But obviously that can't be the case because this is longer. This is longer due to the curvature of space-time. Time slowed down, it went further. So fundamentally, under the general theory of relativity, these are not the same infinitesimals. They're not the same things. So um, there's something different going on here. Time is not infinitely dividable. So what is going on here? Well, what this is called stretching. Stretching. And Infinitesimals can't stretch because you got an infinite number here and you got an infinite number there, and infinity equals infinity between the limit of one here and the limit of one there. You're talking about the same number of infinitesimals. They're the same. But obviously this is longer. This is stretched. So infinitesimals can't explain this situation caused by general relativity. Because you can't have the same number of infinitesimals explain a longer distance traveled in the same amount of time. That requires an explanation of stretching. Stretching. Can infinitesimals stretch? No, because it's the same number of infinitesimals. But there's obviously got to be more of them. Well, how could there be more of them if it's the same number? Well, if the infinitesimals can't stretch, that's the problem. What can stretch? What is stretching? Stretching is using the same number over a longer distance. That's what stretching is. Well, infinitesimals can't stretch. There's an infinite number here, and if these were the same infinitesimals down here, they would only go this far. They couldn't go this far and still be 0 to 1, 0 to 1. Infinitesimals don't have a distance that you can double in size. They can't stretch. There's always the same infinite number of them. They can't stretch. You can increase the number of infinitesimals, for instance. You could go, for instance, you go from 0, 1 to 2, double your infinite sets of infinitesimals. Set 1 and set 2. You can double the number of infinite sets of infinitesimals. But that's not what's going on in general relativity. It's time that is stretching over a longer distance. Time is slowing down. See? So you don't, this little trick here doesn't get you out of the problem of general relativity. These infinitesimals have to be the same as these infinitesimals in order for time to slow down under general relativity. But these infinitesimals are not the same as those infinitesimals. Clearly, they're not. These are stretched, but you can't stretch infinitesimals. Therefore, you have to have something that's capable of being stretched. And what's capable of being stretched is quanta. Quanta meaning a discrete indivisible unit of time in this particular case. Quantum mechanics is named after this concept of indivisible units of matter. But it's an indivisible unit. And it's not an infinitesimal. You can't divide a quanta or an indivisible unit into smaller pieces. You can't. Now, I understand that there's geometry issues with that, and these things cannot be imagined. But nonetheless, that is the case. Quanta can be stretched in the sense that quanta can come in relatively different sizes. So you can have a quanta that's bigger than another quanta, for instance. So quanta they're stretchable. So you can have something like this, and then something like this, both indivisible, but different in terms of relative size. And that's what's going on when time slows down under general relativity. It's being stretched. It's the size, the relative size of the quanta compared relative to another quanta is changing. Uh, in terms of relativity, it's either being compressed or it's being stretched um, relative to something else. The thing itself doesn't realize it's being stretched or it's being compressed, but relative to something outside its local area, in comparison, that's exactly what's happening to it. So, uh, quanta is the solution to this problem. So, uh, in these two scenarios where you are traveling a greater distance at a faster speed because time has slowed down due to the curvature of space-time, what's happening is the quanta of time is stretching as opposed to adding more infinitesimals down here, which is not the case, or stretching infinitesimals, which is not possible because you always have the same number of infinitesimals, an infinite number. But what you get is a stretching of quanta. So, uh, you may have, just say, 1, 2, 3, 4 quanta of time. Down here, you have the same thing. 1, 2, 3, 4, except they stretch. So they're taking up more time, or the quanta of time has stretched. The relative size of it compared to something else, it's bigger. Um, so because infinitesimals can explain this stretching of time due to the curvature of space-time, to solve the problem, you need quanta. And quanta are indivisible units. So it's not an infinite number. It's a finite number of quanta. And each quanta is indivisible. So uh, this explains why time itself cannot be divided into an infinite number of moments of time. It's in fact quanta of time. Um, and you know, it, it's just more proof that infinities don't exist in physical reality, and that mathematical models don't necessarily apply to reality. I mean, the mathematical model of the infinitesimal or infinite sets, um, while mathematically true, doesn't apply to reality, which shows that there's this fundamental relationship, inverse proportional relationship between time, traveling through time, and the velocity of an object, uh, which has to equal to the speed of light. Quanta is how you explain that, not mathematics, not infinitesimals. Um, so, when you're trying to think about reality, be careful of mathematical models. They may be great mathematically speaking, but they do not reflect reality. All right. I know this is complicated and very abstract and difficult, perhaps, to comprehend, but I think you can get the idea of what I'm saying. So, if you have any questions, leave them below. I'd appreciate it if you press the subscribe button, and In terms of the divisibility of time, time is not infinitely divisible. All right. Take care, guys.